Thank you very much. As she said, it's wonderful for me to be here. I'm with the University of New Mexico Physics Department, and I'm going to talk to you about discovering new particles. And this is a picture of what physicists look like when they think they're about to discover a new particle. This is a picture that was taken in the control room of the experiment I work on, the ATLAS experiment at the Large Hadron Collider in November of 2009. That was a very exciting time then. That was 2009. We didn't actually discover a particle that day. That was the day that the collider, which had been in development since 1995, so almost 2 decades, that was the first time that a particle went around the ring successfully. That was a big step. In 2012, there was a big announcement. At that time, on the 4th of July, by coincidence, 2 international experiments, one of them being the ATLAS experiment that I work on, and the other being the CMS experiment, who are our friendly competitors on the other side of the facility. 2 international experiments simultaneously announced the discovery of the Higgs boson. Has anybody here heard about the Higgs boson? Yeah, okay. So it was a real positive thing for our field. And again, that was the culmination of a project that had begun 20 years earlier with the formation of those collaborations in 1992. So here's a picture of the spokesperson for my experiment making the announcement at 9 o'clock in the morning in Geneva, Switzerland, which is where the collider facility is. And 500,000 people around the world watched that presentation streamed live. 500,000 people thought it was worthwhile to check into that presentation. Here's a picture of 700 people who gathered in a conference hall in Australia on the other side of the planet just to watch her make that announcement. At the same time, now bear in mind, this was going on at 9 a.m. in Geneva, which is 8 hours ahead of New Mexico. 250 people were interested enough to gather in a conference hall in Chicago. It was 2 a.m. for them. There were 1,000 television stations and 5,000 news programs that felt it was worthwhile to show video footage of that announcement. It was a really big deal. Here's a picture of people gathered in Germany watching the live stream. Here's people watching in Japan the live stream. Here's people in California, really sleepy people at that point, watching the live stream. It was a big deal, the discovery of the Higgs boson. Why would people all over the world, why would people all over the world stop what they're doing, wake up in the middle of the night, drive to Fermilab out in the middle of the countryside in Chicago to watch an announcement about the discovery of a particle? You know how many particles we have? I brought this book to show you. This is the book that all the people who are in my field, who are experimental particle physicists, keep on their desk. It's all of the particles that we already know. It's 1,700 pages, and it's small type. We got a lot of particles already. So here's one page from this thing called the Particle Data Book. This is just a few of them, and this is a copy of that page from Wikipedia. So the question is, do we need another one? Why would we need another one, and why would we be so excited about the discovery of another one? Do we really need to know about any more particles? And my answer to you, and that's what I want to develop in this talk, is yes, we actually do need to know about more particles, despite the fact that we have 1,700 pages worth of particles already. And what this talk addresses is, what are particles? Why is discovering new particles important? What can a particle tell us about the nature of the universe? And what might be discovered next? Particle physicists, and I'm one of that community, are in the business of finding out the content of nature's cookbook. What we want to know is, what's the full set of ingredients that nature has in its pantry? And even more importantly to us, what are the rules that nature uses in its recipes when it combines those ingredients? Particles and forces are the ingredients. I'm sure you know some particles already. One of the common particles that many people know of is the electron, the stuff of electricity here. Another common one is the photon, the particle of light. All of the most fundamental particles that we know of have the interesting property that they occupy no volume at all. I don't mean they're really, really small. I mean, no matter how closely you look at them, if you get the world's best microscope, if you invent a new microscope which is even better than the world's best microscope, they occupy no volume at all. They're what we call point-like. Well, what's so weird about this is they have mass anyway. They have something like weight anyway, and they're fitting it into no space at all. When fundamental particles like that bind together in clusters, so we call that bound states, of 2 or 3, we sometimes also call those clusters particles. That's a little bit bad choice of language on our part. We should really call them something different. We should be careful to call them bound states, but we sometimes call them particles too. So here's a picture of a bound state of 3 of those fundamental ones. That's a picture of a proton, close up. You've heard of protons, you've heard of neutrons. We typically also call those particles, and they're also in that book. They're not point-like. They have some physical extent because there's some space between the constituents there. But I just wanted to be clear that when I talk about finding new particles, I'm talking about 2 different kinds of things, finding these point-like ones and also finding bound states as well. Well, it turns out that of those point-like most fundamental ones, turns out that there don't seem to be very many of them. Here's a picture of all of the ones that we know of at this time. This is the complete set of point-like fundamental particles. Now, those other ones that I mentioned, those bound states, those clusters, they fill up the other 1,699 pages of that particle data book, and they're still interesting to study. But what I'm going to talk about right now are these point-like fundamental ones, which are indicated by this small number of colored blocks here in this graph. So I'll just mention something about a few of the ones that you see in this table here. So you see matter like us, is made up of 6 things that are called quarks and 6 things that are called leptons. Now, not all of the quarks actually seem to be needed to make up us. We're made up of only the 2 on the left here called the up and down quarks. They happen to be the lightest ones of this family. And to complete the construction of an atom, you need not only the nucleus in the middle, which is made of those quarks, but also some electrons orbiting outside. So there's the electron. And then there's some of these other particles which are very similar to the electron, but just heavier. And we're not exactly sure what their role is in nature. We know they exist, but they don't seem to be needed in order to make the material world that we know about. There's also another kind of a particle that you may have heard of called antimatter. It does exist. It's not in this table because it's not typically classified as a separate type of fundamental particle because there's one of the antimatters for every one of them that's in here. Here's that same table. I just want to talk a little bit about the things that are in this category called forces. So one of the interesting things that was discovered by fundamental particle physicists is that forces like electrical force, electrostatic attraction, gravitational attraction, we think of them as some kind of a wavy thing that transmits across space. Turns out that they're also particles. So I can put them in this table with the fundamental particles, even though they're forces. So this Greek gamma symbol here, that's the photon. The photon, the particle of light. It turns out that it's not only the particle of light that we use to illuminate this projection screen, it transmits the electromagnetic force. It communicates the electromagnetic force between any two charged particles. This lowercase g here, that represents the particle which is called the gluon. What a funny name. The reason it has that name is because it's understood to glue the nucleus together. The nucleus is made of protons and neutrons. The protons you might have heard of have positive charge, which you would expect would cause them to all repel and not want to stay in the nucleus. But we know that they're in the nucleus is stable, something must be gluing it together. That's the gluon. It transmits the strong force between any two quarks. Down here, there's two particles called the capital W and the capital Z, and they're responsible for the weak force. That's what produces radioactive decay. Notice that in this, in this fundamental graph, there's no particle to represent the transmission of gravity, even though we do recognize that there is a fundamental force called gravity. That's because there's a big question waiting to be solved, especially by the young people who are here. The question is, what does gravity have to do with all of the other fundamental forces? We don't really understand how mathematically, how theoretically to relate it to the other forces which are indicated here. If it's like the other forces, we would expect there to be a particle called the graviton that would transmit gravity, just as the photon transmits electromagnetism. There are experiments which seek to find the graviton, but it has never been found yet. So that's a big open question. That would be a great particle to discover. So I'm not going to drag you through the whole table there, but I'll just point out that there are some particles listed there that I haven't really talked about. There's the C, the S, the T, the B. Those are all heavy quarks. It's a mystery why they exist, because the C is just like the up that we do need for constructing the nucleus. But it's just heavier. And the T is just like the up, but it's just heavier still. Why does nature have these ingredients on the shelf, but it doesn't seem to be using them too much? There seems to be some strange replication. So, and similarly, there are these nus and this mu and this tau, et cetera. They've all been observed. We know they exist. There's no doubt about that, but their role in nature is unclear. And then there's this other thing here, this H, this Higgs boson. I'll talk more about that later. That's the one that all the hundreds of thousands of people watch the stream about. Now, there have been additional particles proposed, but until they're observed, they don't get to be in this picture here. Until they're observed, they're what's called beyond the standard model, or in the jargon that we use when we talk about this in physics meetings, BSM, beyond the standard model. And what's in this table is what's called the standard model of particle physics. So what I want to talk to you about today is searching for new things, seeing if there's stuff that belongs in this table that hasn't been found and hasn't been put here yet. I want to talk about searching for new things, and it is fun to find them, but what's most important to particle physicists is not just finding new things, it's seeing if they form a pattern. So it's not like we have an album for our stamp collection and we got to keep finding new stamps to fill up our album. It's what does the pattern of those particles tell us about fundamental things about the universe? So the key word for this slide here is pattern. We're interested in looking for patterns. Well, you already see some curious patterns here. I think that anybody can see that there are some things that just scream out at you as hints that there's something going on in the universe that is forming multiplets with interesting similar numbers of constituents. So you see here that there's 6 quarks, and 2 of them, the ones that we need to construct the material universe, are replicated by 2 other heavier pairs. And the light lepton pairs, the electron that we need and its partner, the neutrino, are similarly replicated by heavier lepton pairs. And altogether, there's the same number of quarks as there are leptons. What does that mean? And all of these building blocks, these quarks and leptons, they come in even numbers. What does this mean? So the key idea for this slide is that there are apparent patterns that are impossible to ignore among the particles that we already know. Here's why we're interested in patterns. Back in 1915, a mathematician named Emmy Noether showed that observed patterns, and the word she used at that time would have been translated as symmetries, but she meant patterns. Patterns indicate that there's some quantity being conserved. But what does conservation mean? Conservation means you can't lose it. It can change form, but you can't lose it. For example, energy is conserved. That's something that would have come up for students who are in an introductory physics class. Energy is conserved. If you have a certain amount of energy, you can transform it into heat, into sound, into motion, into mass. But in the end, if you're very careful and you keep count of all of it, don't let any of it, kind of get lost from your experiment, it'll be conserved. So it can't be lost. There are a number of things in nature which are conserved like that. For example, here's one of them, the conservation of angular momentum. So angular momentum has to do with the rate of rotation of an extended object, like a basketball. So if I had a basketball here, and I had it spinning on my finger, and I had no friction between it and my finger, so once I got it started, it could spin forever. It would not, we would be surprised if after a while it suddenly sped up, right? We would never expect that. And if there was no friction, we wouldn't expect it to slow down either. We would expect it to just spin forever at the rate at which I started it rotating, right? That's because angular momentum, the rate of rotation of an extended object, is conserved. What does that tell us about a pattern, about a symmetry? I said that when something is conserved, it means there's some kind of symmetry, some kind of pattern. So suppose I visualize this basketball here, and it's got the Spalding label on it. The Spalding label is going around on the equator of the basketball. If it suddenly, just as the Spalding label was facing that way, if it suddenly sped up, I'd say there must be something special about that direction in the universe. When things point in that direction, they speed up. So there's something special over there. The fact that it doesn't speed up when it points that way, that it keeps rotating at the same rate forever, says there's nothing special about that direction or any direction in the universe. The universe is symmetric in direction. The universe is isotropic. So we can relate something that's happening locally to this basketball to a feature of space itself. Space itself is isotropic, and we find that out because angular momentum is conserved. So that's why we're interested in things like conservation of angular momentum, or in general, conservation of anything, because we can use it to find out really big deal things about the universe, like space is isotropic. So that's what this picture is supposed to tell you. Conservation of angular momentum tells us about the isotropy of space, which is a symmetry of space. So the message of this slide is that when we see a pattern, we should suspect that there might be a conservation law. Here's a picture of Dr. Emmy Nether. Her theorem has been called one of the most important mathematical theorems ever proved in guiding the development of modern physics, fundamental on a par with the Pythagorean theorem. Why we're interested in these conservation laws? Again, they reveal that phenomena that might seem different are really just alternative forms of the same thing. For example, as I said, once we know that the law of conservation of energy is true, we see that heat and light, vibration, momentum, mass are not really different. They're all different forms of the same thing. So we get a unification of our understanding. We get a unification of phenomena when we see conservation laws, when we see patterns. That's why we're interested in patterns. The unification of phenomena turns out to be a philosophical ideal that particle physicists, and maybe other physicists as well, typically have. We have this feeling that maybe the grand diversity of the universe, the fact that there's plants and animals and inanimate rocks and stars and all this stuff, this amazing diversity, maybe it really all flows from a single field, a single thing which in different realms at different times takes different forms. That's what's suggested. That's one of the things that's suggested by this image here, this image of the history of the universe. This is the Big Bang here on the left, and you see coming out of the Big Bang all kinds of diversity, so that once you get to now, which is the far right, we have people, we have stars, things on vastly different scales. We have black holes, we have possibly massless particles, incredible diversity. But we see that a little bit earlier, well, those people are made of atoms, and those atoms, some of those atoms were born in supernovae. You've probably heard that the supernova expelled heavy nuclei, which eventually were gathered gravitationally and make up parts of the organisms on the Earth. So something like a supernova could lead to the life forms on the Earth. But before the supernova, we had the particles which were gravitationally attracted to form the star that then exploded in a supernova. And before we had those atoms, we have their constituents. Here are these bound states, like the proton, the 3-quark bound state, the proton here, or the two quark bound states that I mentioned. And before that, when the universe was younger and hotter and smaller and denser, there were the free quarks themselves, which composed those bound states. So here are the free quarks Q, and some of those leptons, like the electron and so forth, going back all the way to the dawn of the universe. So we have this philosophical ideal that maybe if we could point back or maybe reconstruct some little example or event which was similar to the Big Bang, we might have a sense of what things were like at the dawn of the universe. And it turns out that in many cases, the evidence for a conservation law, which could lead to this kind of unification of our understanding, often that evidence is a particle. So what I want to talk to you today about is just 3 or 4 or 5 examples of really big questions, things that are just hitting us over the head that we don't understand about the universe, that could be answered if we just discovered a particle. That's why we're so interested in discovering new particles. So here are some illustrations of that. I want to go back and think about some of those patterns that we saw on that that graph with those the quarks and leptons and so forth. So one of the things that we noticed was there were 6 quarks and 6 leptons. Does everything come in 6s? Or is this a sign instead that quarks and leptons are really not different? They're just different forms of the same thing. Right now we think they got to be really different because the quarks are inside the nucleus and the lepton, the electron is going around the nucleus. They seem like really different things. They have very different masses. The lepton is very light, has almost no mass. The quarks can be very heavy. They seem extremely different, but maybe they're not. Maybe they're the same thing, but in some way just with different, showing us different faces. One way to find out if they are the same thing would be to look for particles that are predicted by the so-called grand unified theories. Those theories say that it may be possible to transform a quark into a lepton with another particle that's called the X. So here's a picture of how that could happen. Here's the proton, which I said was made up of a bound state of 3 quarks called an up, an up, and a down. So think of those quarks as being attached to the ends of these lines. And time is flowing from left to right. As time goes on, well, the down quark doesn't do anything. It just lives. But the 2 up quarks annihilate. At this point in time, they go out of existence, and they turn into one of these hypothetical X particles, these grand unified particles. And it lives for just a very short time, and it transforms itself into a lepton, a positive electron, and something else, another type of quark. But the point is that where we had 2 quarks here, all of a sudden we've only got 1 over here. This X is telling us that there's, in some sense, some equality between the leptons and the quarks. That would be interesting if that was the case. We'd find out that nature doesn't have 6 quarks and 6 leptons. It's got 12 of the same thing. So for us, for physicists, that would be considered an improvement. Now, how do people do that? How do people look? The goal is to find the X particle. It's thought to live extremely briefly, so there's no camera in the world that would actually be able to photograph the X itself. So what we have to do is look for it indirectly. What we do is we expect that if it did exist and it lived for a short time in the right environment, it would produce a spark of light. And that would be the evidence for what's called proton decay. On that picture before, the proton was the thing going out of existence. It was up, up, down, and then after a while it didn't exist. We call that proton decay. Here's an experiment which was constructed under a mountain in Japan called the Kamiokanda experiment, in which the experimenters collected an enormous amount of extremely clear water in this tank. So these physicists are in a little boat on the surface of the water, which is very deep. And what they're doing is maintenance on this enormous array of detectors which can detect extremely tiny amounts of light. And they're waiting for the event in which one of the protons in that tank of water is made of protons, one of them undergoes this proton decay process because there's an X particle. And if one of those protons decays, it'll produce a flash of light that would be recorded by those sensors that cover the wall. And if enough of those happen consistently in a way that we can be sure that what really happened was the X particle and not that the sensors got an electrical short and they're not working right. If enough of that happens, we would then be able to infer that the particle X in fact exists, and we would have some evidence for the unification of quarks and leptons. So that's one example of a particle we would love to find. I actually worked on that for, not in that particular experiment, but in a very similar one deep in a salt mine under Lake Erie near Cleveland, Ohio. just sat in that salt mine, waiting for that flash of light. It didn't flash while I was there. We still haven't found the X particle, but every grand unified theory now predicts that they should be there if we have the technology, the technique to find them. Just still thinking about those patterns, could they help us to understand dark matter? Has anybody heard of dark matter here? Okay, so what you know is, what you've heard is that there's evidently some stuff in the universe which is hypothesized to exist because it does a number of things which have been clearly observed by astronomers. One of the things that it clearly does is it bends the paths of light. So this is the dark matter. We can't actually see it, but that's what it would look like if somehow we had eyes that could see dark matter. There it is, and its mass is deforming the space-time manifold in a way that causes light emitted by this star here to curve around the dark matter cluster. And then here's the Earth down here, so that when an observer on the Earth views this, they don't know it was bent, they don't know it was curved. They point their eye back towards where they think it came from. They think it came from there. So if this star is producing, it's not just producing that one beam of light. Of course, it's producing beams of light that cross over the North Pole of this dark matter object and that come and bend on the left side and so forth. And so what would actually be observed on the Earth is not just a single point of light over here, but an arc. And this is a photo actually taken by NASA of one of those arcs. And that's telling us that there must be some dark matter over here somewhere, because all of these are images that are coming from the same star, but it's been spread out and bent in this way. So the interesting thing is that it turns out that there's more than 5 times more dark matter than normal matter in the universe. You might have heard this. It's thought that everything we can see, everything on Earth, everything we can see out in the cosmos, only constitutes 4.9% of everything that there is. 5 times more of the stuff is dark matter. Well, wouldn't it be great if we could find that? We'd really like, I mean, that's a big open question, and we would love to know more about what it is.
Shouldn't we call them us abnormal matter?
Yeah, exactly. Yeah, right. Yeah, we're the minority of the material. You're right. So, could we find this dark matter? Is it hinted at somehow in those patterns? So we think we see a pattern of 6 quarks and 6 leptons, but maybe that's actually not a pattern. Maybe there's something missing from our table. Maybe there's more than 6 leptons, and maybe we just haven't found them all, and maybe there's one that we haven't found, and it's the dark matter. So one of the kinds of things that particle physicists look for is extra leptons, new leptons. Here's a picture from New Scientist magazine from remarkably exactly a year ago, 25th of February 2014, titled "Fresh Hint of Dark Matter Seen in Neutrino Search." It turns out, and I'm not an astronomer, but what they're telling us is that when astronomers looked at the light coming from this particular region of the universe, and they focused not only on where it was coming from, but what color it was, the frequency of the light, what color it was, they postulated that the color of the light could have been produced by a previously undiscovered neutrino, that's one of those leptons, of a mass 7 something or other, that had transformed itself into photons. So if they're right, which this hasn't been fully confirmed yet, if they're right, maybe the dark matter has been seen, not just indirectly by the way it bends the light gravitationally, but maybe more directly in its product of photons. So that's another example of a particle we'd love to see, the dark matter particle. Here's another one. So I'm still thinking here about patterns and unification. You might know that there are 4 fundamental forces: gravity, electromagnetism, the strong force, and the weak force. We might wonder, when we're thinking about unification, are there really 4 fundamental forces? Or is there one fundamental force, and in different epochs, in different eras, in different realms, it just seems to be different? It seems to be the electromagnetic force in some realm, seems to be gravity in another realm. Might it actually be that there's really only one force? That's a big question that a lot of particle physicists are interested in. Might those 4 forces be unified as a single force? Here's what's making them seem disunified right now. They each have their own characteristic strength, and their strengths seem very different. The strong force, the one that holds the quarks in the nucleus, it's the strongest. It's very strong. It's got to overcome the electrical repulsion of the protons. Gravity is very weak. Even though gravity is obvious in our daily life, it actually turns out to be way weaker than the strong force. And in between the strength of gravity and the strength of the strong force is electromagnetism and the weak force. So they're very different. They seem different. We call that the strength of the force. The technical name for that is the coupling. The strength of each coupling, it turns out, depends on the ambient energy. Now think about the expansion of the universe from the time of the Big Bang, when the universe had no dimension at all. It was all compressed into a point, through the expansion till now, when it's really big. All the energy has always been there. So in the early universe, it was really dense and it was really hot. And then when it was middle-aged, it was middle-sized and a little cooler. And now it's really big and really spread out, so it's pretty cold because all of the energy has been dissipated throughout the universe. At early stages of the universe, when the universe was hotter and smaller and the density of its energy was higher, we would expect the couplings, the strengths of the forces, to have been different because the couplings depend on the ambient energy. So we know the strengths of the forces now with the temperature of the universe as it is now. We know how they depend on energy, so we can extrapolate them back to the moment of the Big Bang. And when we do that, we get a graph that looks like this. So this graph on the horizontal axis is time running backwards. So now is where this dotted line is on the left side of the graph, and to the right is going back in time to the time of the Big Bang. And on the vertical axis is, strangely, it's the strength of the force, but it's 1 over it. But don't worry about that. The point is that it's related to the strength of the force. So right now, the electromagnetic and weak and strong forces have very different strengths. That's what you get by seeing that they cross this dotted line at different points, differing by a significant amount, by tens or thousands. The strength of the force depends on the number of particles that the force could affect. So I said we could extrapolate back into time the strengths that the forces would have had in the hotter, denser, earlier universe. If we extrapolate and assume that the universe doesn't actually have any other particles than the ones we currently know about, and we extrapolate back to the Big Bang back then, we see that the strengths of the forces, even at the time of the Big Bang, were a little different. Those colored lines don't come together at the same value. So they're a little different even at the dawn of the universe, if the universe doesn't actually include any other particles than the ones we know about already. But what if we hypothesize that there is a class of particles in the universe waiting to be discovered called supersymmetric particles, SUSY in the jargon, supersymmetric particles? In that case, here's what that graph would look like. The extrapolations turn out to be just a little different. And if supersymmetric particles exist, this is the extrapolation with supersymmetry, then at the birth of the universe, all of the forces have the same strength, and we wouldn't be able to tell them apart. We wouldn't be able to tell the electromagnetic force from the strong force if we were able to be there at the birth of the universe, because they would have exactly the same strength. Supersymmetry is this theory invented about 35 or 40 years ago that every kind of particle that we know of now has a partner with a different spin. That's a fundamental, sort of technical, fundamental property of a particle. Now these hypothesized partner particles, and they haven't been observed yet, they're one of the things we're looking for, they have amazingly silly names. So one of the particles that we actually know about, remember the weak force is carried by the Z. Well, if its supersymmetric particle exists, it's called the Zeno. One of the particles we actually know about, the quark, if its supersymmetric partner exists, it's called a squark. And my new favorite, the one that I just started doing some research on in the last month, is called the Goldstino, which is distantly related to Professor Goldstone at MIT. So particle physicists, there's a lot of activity right now at the Large Hadron Collider and elsewhere looking for these supersymmetric particles. And one of the reasons is because it would be amazing if all of the fundamental forces that seem so different in our daily world now were really only one force.
Where's gravity?
Oh, thank you. Remember back on like slide number 5, I said I don't even have gravity in that big black graph because it's not a part of the standard model. It's so poorly understood right now that it's not in any of our graphs, unfortunately. I'm sorry.
All those lines on that previous graph had a break in the slope. Is that all at the same energy level?
You know, I didn't make this graph, and I don't know all the details about it, and I only grabbed this graph in order to illustrate this particular point. So I'm sorry, I can't answer that. Sir, that was your question. Yeah, I'm sorry. I don't.
Why should that force exist at that particular time?
Yeah, I can't.
Make that particular bend. It seems like a legitimate question.
Yeah, I can't actually comment on that. I'm sorry. Yeah. I want to pause here and say that not observing a particle can be just as important as observing a particle. One of the most, in my opinion, misguided pieces of science journalism ever written by Mr. Malcolm Brown, a great journalist, published in the New York Times in January of 1993. It was written about a groundbreaking measurement by the CDF collaboration, and the article was titled, 315 Physicists Report Failure in Search for Supersymmetry. I'm still mad about that one. That wasn't a failure. I don't think he got the point that the fact that there was an existing theory about how supersymmetry should work, and people focused on what its signature might look like and found that its signature wasn't precisely what the theory suggested it should be, that's not a failure. That's an indication that the theory needed to be improved. Far from a failure, that tells us that the relationship between matter particles and force particles, or the particles with different spins that I mentioned, particles in supersymmetric particles, is more subtle and more complex than our first simple models. That was a major advance in our understanding of the relationship between matter and forces. And I would say that the New York Times got that wrong. So the point I'm making here is that when we look for a particle, we're not engaged in stamp collecting. We're not trying to find the 501st particle to put into our album. On the contrary, the presence or absence of every particle has the potential to tell us something foundational about nature. Some particles are hard to find now because they were abundant in the hot early universe, but they're just less common in this cold later era. That doesn't mean that they're not still in the rule book, still in the recipe book. And so we want to study them because we want to understand nature's recipe book. It would be sort of saying that we're looking for a particle which is harder to find now in the cold later universe would be like saying we're looking for sunflowers in February. The idea of sunflowers does exist. They do exist, but they're in the summer when it's hot. It's hard to look for them in February. But if we were making a catalog of particles or of flowers, we need sunflowers. So what we really would like to have would be something like a time machine that could replicate the conditions of the early universe. If we could replicate that, we could replicate the particles that existed back then, and we would get the whole spectrum of them. It turns out that with modern technology, we can indeed replicate the conditions of the early universe. We can replicate the conditions of the universe 1/1000th of a second after the Big Bang. We can build a machine that can concentrate a lot of energy in a small space. So it's a little replica of that hot, dense Big Bang. It's a little replica of the early universe. And when we make that replica, we then look to see what kinds of particles naturally form in that machine, in that early universe replica. And the interesting thing we find is there's not an unlimited variety. Nature does seem to have a limited set of ingredients. Yes, please.
If you concentrate all this energy in a small space, wouldn't that replicate the Big Bang as in?
Yeah, well, that would cost more money than we have. You know, these machines, which I'm going to talk about, the one that runs on Long Island, it could, on bad days it can brown out. It can use so much energy that it has the potential to brown out the neighboring town, if it weren't handled properly. So they use an enormous amount of energy. So you're right, but we don't want to use all the energy.
Is that what they were trying to replicate at the CERN?
Yeah, exactly. That's what I'm going to talk about here. Exactly. That's what these colliders are for. These colliders that you may have heard of are time machines in this sense. So the interesting thing is, when you give nature a lot of energy and replicate the Big Bang pretty satisfactorily, you find that still nature does not create just any old thing. It seems to forbid certain things from existing and permit other things. And what we do is we take notice of what is nature allowing to exist, what is it not allowing to exist, and from that we infer what are the rules that nature is using. So here's one of those energy concentrator machines which you have already foreseen is the colliders that I was talking about. So take two hollow circular pipes with diameters of a few miles, 17-mile diameter here. Place one of them above and one of them below, and put common particles into both, ones that are pretty easy to find just about anywhere. So protons, we got protons all over the place. So put protons in the lower ring and make them circulate, well, what would that be, clockwise. Put protons in the upper ring and make them circulate counterclockwise, and make them circulate at speeds of almost 1 billion miles per hour, and now divert their paths so that, so that there's actually a little connector, a place where these protons from the upper ring can collide with the protons from the lower ring. So add that little connector, make them collide, make those protons collide, and they will annihilate at a few select points. When two protons collide, they produce a fireball. And that fireball has energy, which is the combination of their masses, which is like their weights, plus their momenta, which is like their velocities. So the individual masses, the individual weights of a pair of protons is really pretty small. But when they travel at 1 billion miles per hour, their velocities are really high. So their momenta are high. So they have a lot of energy just because of their velocity. So they're traveling at 0.9999 blah, 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 times the speed of light. They have huge momentum. And when they collide, the energy of that fireball is the amount of, it's equivalent to the amount of energy stored in 8,000 protons. So that fireball is what I am referring to when I talk about a small replica of the condition of the universe 10 to the minus 12 seconds after the Big Bang. Here's an image of what that might look like. The largest such device is, in fact, the Large Hadron Collider in Geneva, Switzerland. So here's a picture of the 17-mile diameter collider just for scale. Here's the runway of the Geneva airport. And this was commissioned in 2009. You saw that picture of how excited people were on that day. And data taking started on 2011. And there are hundreds of US physicists working there, including students, including UNM students, in fact. So we collide protons against each other at 4 points. One of them is called LHCb. That's an experiment. One of them is my experiment called Atlas. Then there's another one called Alice or Alice, depending on if you're one of the Italian collaborators. And one of them is called CMS. And where those collisions happen, a fireball is produced every 25 nanoseconds. So those fireballs are produced, like a lot of fireballs are produced every day, every moment. And we feel that there's so much energy in each of those fireballs, basically almost everything that was present in the early universe should be able to be produced in that fireball. So the cookbook is open. All the ingredients should be available. Or another thing people say is that everything not forbidden is compulsory. And then we look very carefully at those collision points and try to find those particles in the tracks that exit the fireball. So we're looking at tracks like this that are coming out of the fireball. We're trying to image them and see were there unusual particles in those tracks. So this is what we use to watch for them. Just like the collider itself, the detectors we use are enormous. So here's a person. Here's a person before the detector was finally closed up. This is the Atlas experiment, the one that the University of New Mexico group works on. You could think of it as the world's largest camera. It exists to make images of those particles that are produced in the fireball. Atlas and the other 3 detectors at the LHC are located up to 175 meters underground. So here's the surface in Switzerland, Lake Geneva, fairly shallow. And then 175 meters underground, there's the actual collider ring. It's not on the surface at all. And there's the experiment. And here's a semi-technical drawing of what Atlas looks like down there. You saw how big it was, so you can imagine this is the whole thing, and we just had a photo of a part of it. And the way it was assembled, people say, was like constructing a ship in a bottle. People had to send the individual components down those shafts, 175 meters, and build this thing in its place it can't be moved. Now that it's there, it's there. Parts of those detectors, parts of what was sent down that shaft and installed, were built with the help of students at UNM. So this is one of the technical pieces of the Atlas detector. It's being pushed into the very heart. It's called the pixel detector, and it tracks the most short-lived, rarest particles that are produced in the collision right after they're produced in the heart of the fireball. So UNM are members, along with 2,995 or so other people, collaborators on this experiment, which again takes place in Geneva, right there in the center of Europe. Collaborators are drawn from every continent except Antarctica. 70 institutes from about 30 nations come together. Here's a very small part of my collaboration. This is only 10% of my experimental collaborators here. This is a photo taken in the office space at CERN. So the most famous particle discovered in the 21st century was the Higgs. You know about that. We found it. And the Higgs, I can't talk to you about particles without having at least one slide here about the Higgs. I do want to tell you a little bit about the Higgs. The Higgs field gives mass to all of the particles in the universe. It fills the universe, causing drag on everything in motion. It's sort of like molasses, but invisible. So that when particles move through it, they experience drag as inertial mass. Responding to it, yes, so thank you for asking that. So the Higgs field here, it's like a tank of water or a tank of molasses, and you feel in it the way you feel when you try to run underwater. You feel heavier, you feel more massive. This field can condense into particles, and the condensate of this field is the Higgs boson. So sometimes we talk about the Higgs field, sometimes we talk about the Higgs boson. We mean the same thing. You could also think of the particles as ripples in the field. Here's a technical picture I just wanted to show you about what was the graph that our spokesperson was showing in that first announcement. So here's a picture of a simulation of, actually I think this is data, of a collision. So what you're doing is you're looking down the beam pipe. So the protons went into the screen here, and the other protons came out of the screen, and they collided right there in the screen. They made their fireball, and then all kinds of other particles came out. So that's the beam's point of view of the Higgs decay. So how was that Higgs actually produced? Well, when the protons are zooming along in their tunnel, they're being held together by those gluons. Remember, the gluons are the strong force particles that hold protons together. So it's not just a beam of protons, it's a beam of protons and gluons. And when you get a collection of protons at the Large Hadron Collider, it turns out that there's actually more gluons than protons in that packet. So a lot of the collisions are actually gluons colliding with gluons from the other beam. It's actually gluon-gluon collisions 80% of the time at the LHC. So what this picture is representing is time still is traveling from left to right, and there's two gluons that were going. So this was a gluon in one of the beams. This is a gluon in the other beam that was meeting it head on. And when they met head on, well, they did some kind of fancy dance exchanging some top quarks. But after a while, all those top quarks went away, and they turned into a Higgs particle. So the Higgs existed for a moment in time, and then it itself annihilated, turned back into some top quarks, and then those top quarks turned into photons, the particle of light. So what we look for are collisions that produce two photons. So this graph is searches for anomalously high occurrences of collisions that produce 2 photons as a function of the energy of the collision itself. And well, the fact that there's this smooth exponential curve is well understood, but then there's this little enhancement. That little enhancement that's the signal for the Higgs. So the signal for the Higgs is an enhanced number of decays to 2 photons whose combined energy, so the projection onto the horizontal axis, the combined energy is the Higgs mass. So I'm only going to talk to you about one other particle now. So I have to tell you about the one that UNM discovered. You want me to pause for a second for the video? Okay, so now I can't resist to spend a minute telling you about the particle that the University of New Mexico group discovered. So I had mentioned that particles can help us understand all kinds of puzzles, and one of the things that they can help us understand is how the strong force works. So I said the strong force is the one that binds the nucleus together, holds the quarks together. So the University of New Mexico group has focused on studying particles that are bound states of 2 of those strangely heavy quarks. One was called the C and one was called the B, and I never talked about it very much, but they were in that table that I showed early on. And when the C, the charm quark, and the B, the bottom quark, bind together, they make a system that's called B sub C meson. So here they are. They're both heavy, but the bottom is really heavy. It's really obese compared to the charm. And so here's a picture of them together. So you can think of the charm quark, when they're bound together, as orbiting the bottom quark, sort of the way an electron orbits a nucleus. But there's no electron here. It's just 2 quarks, one orbiting around the other. Now, one of the things that you know from your physics class that you've had already is the way things work when it's actually an electron that's orbiting a proton in hydrogen. You know that the electrons, so this is the proton, you know that the electrons can't just be any old place relative to the protons. They have very specific radial distances relative to the nucleus. Do you know that? Have you heard that? The electrons we call them shells. So if there's a proton here, there can be electrons here, this distance, and there can be electrons here, this distance, but not in between. And that has to do with quantum mechanics. The fact that the force that binds the electron to the proton insists that the electron has to be at discrete distances from the proton. So the electrons in hydrogen can be at various levels, and spectroscopically we name those levels. You may have heard of 1s1, 1s2, 2s, et cetera, like that. So what we look at the University of New Mexico is a bound state of the bottom and the charm. So there's no electrons at all. There's just the charm going around the bottom. And this system can take different energies too, even though there's no electron. The quarks themselves form shells. So if the bottom is here at the origin, the charm, it turns out, can be in various shells with respect to it. It turns out that when this system transitions between shells, it actually takes on a different mass, and we observe it as a completely different particle, not just as with hydrogen as an excited electron around a proton, but actually when the charm quark is in a higher shell, the whole system appears as a completely different fundamental particle. And we name those particles spectroscopically too. So the UNM group is looking for those various excited states of the B sub C system. We're looking for occurrences of a bottom quark with the charm quark at various shells, at various excitations relative to the bottom quark. And each one of these excited states that could be observed would tell us something about that shell structure that the strong force has. And then if we find them, when we put that all together, we could understand something about how the strong force binds those quarks together. We look for these particles by using the information that we see in an image like I just showed you a moment ago with respect to the Higgs. Again, the protons collide on axis at the origin of this circle, and we image the tracks in this detector. We use that pixel detector that was built partly by people at UNM. We trace those tracks backwards to their source, require conservation of energy and momentum, and infer the energy and the momentum and the mass of one of these excited state particles that may have been produced in the collision. So in 2012, we got the first one. We observed the ground state. This is just the Feynman diagram for that. So it's similar. We were looking for an unusually large number of something or other that happened at a particular mass. So that was the ground state of this B sub C system. And then in 2014, we got the next excited state. Here's the decay. And again, it was an enhancement, an unusually large number of something or other happening at a particular mass. So UNM also contributed our little particle to our understanding of the world, and now we've got something, you've got an entry in that book too. So here's the last slide. My summary is that a particle can be the key to explaining a pattern. For example, that X particle of grand unified theory could transform quarks into leptons, revealing that they're actually fundamentally the same thing. Or a particle can provide a direct explanation of a phenomenon that's now only indirectly understood. If we could produce at the Large Hadron Collider a dark matter particle, we would no longer know it only indirectly because it bends light. We would know it directly because we would observe it in the lab. Or a particle can lead to a profound unification of parts of the natural world. For example, supersymmetries particles would unify the couplings of three forces in the early universe. Or a particle can provide the basis of a fundamental quantity. For example, the Higgs boson is the origin of mass. Or a particle can elucidate structure in nature. The B sub C2s, an excited state of the B sub C, sheds light on the nature of the quantization of the strong force, like the shells for the electron and hydrogen. So every new particle that we can find has a unique capacity to shed light on the nature of our universe. So every one of them is worth looking for. Thank you.